Hi. As engineers and architects, have you ever wondered if there is a way to quantify the characteristics of your components? Wouldn't it be nice if there is a way for you to quantify your architecture in terms of abstractness, maintainability, developability, and stability? Yes, there is a way to quantify all these aspects of your architecture, which I will be teaching you in this video. I will be talking mainly about component coupling, and I will walk you through the three main principles that govern component coupling, and I will introduce you to several metrics such as the abstractness, instability, and the distance from the main sequence. I will also present you some actionable steps to monitor the quality of your architecture. Let's get started. In component coupling, we are basically discussing three principles that deal with the relationships between components. The first one is the acyclic dependency principle or ADP. As the name indicates, this principle says allow no cycles in the component dependency graph. Let's take two examples and analyze how component dependencies with and without cycles impact its developability and maintainability. If you look at the acyclic component dependency graph on the left, you see all the arrows are pointing in a single direction and there are no cycles. But the one on the right has a cycle between authentication, user and profile components. When the component dependency graph is acyclic, we are benefiting from no stepping over one another during development. We can test and release components in isolation, and there is a proper order to build the components. So now let's see how we can convert the cyclic component dependencies to acyclic dependencies. There are two approaches to break the cycle. One is applying dependency inversion principle, which we learned in the solid principle, and the next is to introduce a new component that both the respective components depend on. Let's see how this is done. Here we have introduced an interface called role to invert the dependency between profile and permissions. So this role interface or abstract class now makes the permissions class in authentication component and also the profile class in the profile component depend on that. So that way there are no cycles in the component dependency. We can also create a new component called role that the authentication and profile components will depend on to remove the cycle. Next principle in component coupling is the stable dependencies principle or SDP. It says depend in the direction of stability. In simple terms, what it says is more unstable components should depend on stable components and not the other way around. So this principle ensures that modules that are intended to be easy to change are not dependent on by modules that are harder to change. Let's now study the stability of a component. Here you can see three components are dependent upon A, while A does not depend on any of those components. So A is a pretty stable component. In contrast, B is a very unstable component because any of those other components could change and trigger B to change. There are several stability metrics that we are coming across in this principle. So we calculate the fan in, which is the number of incoming dependencies, and the fan out, which is the number of outgoing dependencies. And we calculate this metric called instability, which is the ratio of fan out to the total of fan in and fan out. Higher the I, higher the instability of the component and vice versa. For this given component dependency diagram, if we calculate this metric for component C, its fan in is 3 because dependencies come from classes P, Q and R, and then its outgoing dependencies are 2, which are going to classes D and E. So instability is 2 over 5, which is 0.4. When I equal 1, that means fan in equals 0, which suggests that no other component depends on this. So this component is not responsible for any other component, and we say it is irresponsible. And it's dependent as only other components depend on it. When I equals 0, that means fan out equals 0. This component does not depend on other components. So this is an independent component. But as it is responsible for other components, it is a responsible component. So according to SDP, if there is a component A dependent upon component B, the instability of A should be larger than the instability of B. However, not all components should be stable because otherwise the system would be unchangeable. What we actually want is a system where some components are unstable and some are stable. The third principle is the stable abstractions principle or SAP, which states a component should be as abstract as it is stable. There are volatile and non-volatile components in a system. High-level architecture and policy decisions are non-volatile and should be pretty stable compared to user or market-specific components which are volatile and should be unstable. We apply OCP, the open-close principle, which we mastered in solid principles, to extend these stable components without requiring modification by creating them as abstract classes. We also have a metric to assess the abstractness of components. We need two parameters. In C, the number of classes in the component. In A, the number of abstract classes in the component. And the ratio of number of abstract classes to the number of total classes in the component defines the abstractness. When abstractness equals 0, there are no abstract classes, and when abstractness equals 1, all classes are abstract. Next, we come to this important concept of main sequence. As we have already calculated the abstractness and instability, now we are going to plot the abstractness on the y-axis and instability on the x-axis. The main sequence is nothing but the line connecting the point of 1 in instability and the point of 1 in abstractness. Your components should ideally be placed closer to the main sequence line. However, there are two zones of exclusion identified as the zone of pain and the zone of uselessness. The zone of pain is near the origin, which is for highly stable and concrete components. One good example for classes that fall in the zone of pain is database schema. They are not actually volatile and also extremely concrete, and they are highly dependent on. This makes schema updates generally painful. However, we can place stable and concrete utility components like string that are non-volatile in the zone of pain without causing much trouble. The zone of uselessness is around the point 1,1. This is undesirable because it is maximally abstract and has no dependence. Hence, such components are useless. The main sequence is also the line connecting the furthest points from the zone of pain and the zone of uselessness. A component that sits on the main sequence is not too abstract for its stability, nor it is too unstable for its abstractness. Now we can create our third metric to determine how far a component is from the main sequence, called distance, which is the magnitude of abstractness plus instability minus 1. D-value of 0 indicates that a component is on the main sequence, which is where we want it ideally, and the d-value of 1 indicates a component is further from the main sequence, and we will need to re-examine and restructure this component. Next, we can calculate mean and variance for this D metric and identify what are the components that are more than one standard deviation away from the mean or the main sequence. We should try to get those components into the zone of one standard deviation to make our software system easily maintainable and developable. We can establish a threshold for the D value for each component, and we can continue to monitor this value across each release to identify if it goes beyond the specified threshold value and take corrective action accordingly. Now is the action time. I would ask you to create component dependency graphs for the components in your architecture and identify if there are cycles. If so, you need to eliminate those cycles by either applying the dependency inversion principle or introducing those classes that create the cycle into a new component. Next, I want you to calculate instability, abstractness, and distance from the main sequence metrics for each of the components. If there are components that are falling in the zones of exclusion, I want you to refactor. Finally, you need to regularly monitor the d-metric of your components over releases to make sure that it stays within the threshold value you specify. This wraps up our discussion on component coupling, and if you like this content, please like, share, subscribe and comment with your ideas and other topics you would like to learn in the future. Thank you for joining. See you in another video. Until then, happy coding.